Okay, let's unpack this. Welcome back to the Deep Dive. Today, we are strapping in for a high-velocity journey to the undisputed heavyweight champion of our solar system,
The massive gravitational engine.
the true colossus,
Yeah.
Jupiter. And we are analyzing this giant through the lens of one of NASA's most incredible and, frankly, riskier missions, Juno.
It's an essential deep dive for anyone curious about our planetary origins. Because, to truly understand Jupiter is to unlock the fundamental secrets of the history of our entire solar system.
It's that foundational.
Absolutely. Everything about this planet is just a statement of maximum extremes. It boasts the worst radiation environment imaginable, the strongest magnetic field, and it's spinning the fastest of any planet out there.
When we talk about Jupiter, we aren't just talking about another celestial body. I mean, we are discussing an extreme maximal system that forces us to redefine what a planet can be.
It really does.
Our source material makes it clear to even contemplate sending a spacecraft into that kind of environment is, well, maybe a little bit insane.
It's a fair word for it.
To survive the trip and actually get data, NASA had to build what truly amounts to an armored tank.
That analogy of the armored tank is absolutely necessary, and it really defines the mission statement of Juno. For generations, all we had were these beautiful external images, the great red spot, the swirling clouds, and, theories about what was happening underneath.
Right, just looking at the surface.
Exactly. Juno was built not just to orbit, but to pierce that veil. The engineering goal was literally to look inside.
And that is the ultimate goal, isn't it? Peering into the planet's interior.
It has to be.
Because that interior, that deep-seated structure of rocks, ices, and metallic hydrogen, it holds the secrets to how the entire solar system formed, how it got started, and fundamentally, how gas giant planets are truly made.
And Jupiter played such a defining fundamental role, it influenced everything around it from the moment it came into being.
So if we get the recipe for Jupiter right,
we get the recipe for the solar system right. But before we can appreciate the engineering feat that is Juno, we have to grapple with the sheer crushing scale of Jupiter.
I mean, it's hard to overstate its dominance.
It really is.
I agree. Its magnitude is almost impossible to truly frame relative to our own Earth. We are talking about a massive, dominating presence, and that scale dictates everything: the physics, the engineering, and the astonishing story of its formation.
Let's start with that idea of scale, specifically mass. The sources provide a wonderful analogy, the weight analogy, which helps listeners internalize the true dominance of Jupiter.
Okay, let's unpack this. I really want to walk through this comparison because it really stuck with me. We are going to imagine we can weigh the planets on a massive scale, assigning Mercury, the smallest, a weight of 1 kilogram.
Okay, so Mercury is 1 kilogram, light, manageable. Mars is a bit bigger, maybe twice as massive in reality, so 2 kilograms on the scale. Still something you could easily handle.
Right.
Then we jump to Earth.
And this is where the comparison stops being casual. Our 1 kilogram Mercury is now a tiny piece of gravel compared to Earth.
A huge leap.
In this analogy, Earth clocks in at a whopping 250 kilograms worth of rock and water. And that's already immense.
Yeah.
You're certainly not picking that up off the floor.
Not at all. And we leap again to Saturn. The second largest planet in the solar system, Saturn, comes in at 1,700 kilograms on that hypothetical scale.
Wow.
You have to strain your imagination just to hold that much planetary mass in your mind.
But then we hit Jupiter.
7,000 kilograms. That is the moment where the proportional difference becomes not just large, but fundamentally different. Jupiter isn't just a big planet. It is the gravitational anchor of the entire planetary system.
The grand tally is truly stunning, and this is the statistic that I think needs to be screamed from the mountaintops.
It's the one that really lands the point.
If you take every other planet in the solar system, Venus, Earth, Mars, Saturn, Uranus, Neptune, and you add their masses together,
Every single one.
Jupiter still outmasses them all by 2.5 times. That means every other world we know is essentially orbiting in Jupiter's immense shadow.
And that kind of dominance isn't random. It's a necessary requirement for its history. If Jupiter is that huge, it couldn't have taken its time forming. We are convinced that Jupiter had to form really, really early in the solar system's history.
Why the rush? Why did Jupiter need to achieve this critical mass almost immediately, unlike, say, Earth, which took its time to accumulate its material?
It's all due to the environment of the early solar nebula. When the sun was just a young star, the space around it was filled with vast amounts of primordial gas, primarily hydrogen and helium.
Raw material.
Exactly. That was the raw material Jupiter needed to become a gas giant. But that gas, that fuel, it doesn't stick around long. It gets energized and dispersed by the young sun's intense radiation and solar wind on a shockingly short timescale.
So we're talking about a limited window for bulk acquisition. How limited?
In cosmic terms, it's a blink of an eye. Maybe 1,000,000 years, or at most 10 million years. That's the crucial window Jupiter had to complete its initial growth phase and capture the bulk of the gas.
1,000,000 years.
If it formed too slowly, all that material would have been gone, just blown away.
So the implication is that Jupiter had to form quickly enough to be there in time to suck up all that gas and stop it from leaving the system.
Exactly. It needed to reach a critical mass rapidly, a mass big enough that its gravity could overwhelm the outward pressure of the young solar wind and capture that fleeting nebular gas.
And this need for speed reinforces why understanding its damp interior is so critical.
Right. If we can deduce the structure and composition of its core, we can rewind the clock and understand the specific timeline and initial conditions of its birth, which in turn defines the formation history for everything else in the solar system.
It's the ultimate forensic analysis of planet formation.
That's a great way to put it.
So we have this massive, dominant, and fast-forming entity that then settled into a relatively stable orbit, hiding its origins behind a permanent shroud of clouds. To get those answers, to get those forensic clues, NASA had to send in that armored tank, the Juno spacecraft.
This takes us into the astounding engineering required for survival. Sending Juno to Jupiter was, without hyperbole, one of the most challenging missions NASA has ever undertaken.
Just describing the spacecraft itself gives you a sense of scale. It's absolutely enormous.
It is. We are talking about a spacecraft that is close to 70 feet in diameter when its enormous solar arrays are fully deployed.
70 feet.
As it spins and cartwheels through space, it is one of the largest interplanetary spacecraft ever constructed. And that massive size is directly connected to the environment it had to survive, specifically the problem of powering it so far from the sun.
That's a huge point. Historically, deep space missions relied on radioisotope thermal electric generators, or RTGs.
Basically, nuclear batteries.
Right, powered by decaying plutonium. But Juno needed so much power, and it was engineered to be a solar-powered craft, which is just remarkable 500 million miles away.
The solar arrays are necessary because Juno is a flying laboratory packed with instruments that needed substantial, consistent power. But the craft also needed special powers to accomplish its primary mission, seeing through the veil of clouds that perpetually hides Jupiter's internal structure.
So how did the engineers manage to design instruments that could effectively give them X-ray vision?
The entire design is a masterclass in optimization and shielding. Almost all the critical science instruments are situated on the main deck, protected between the gigantic solar arrays. We have particle instruments, an ultraviolet camera, and the analytical core for interior analysis, the microwave radiometer, or MWR.
And the MWR is the key to penetrating the atmosphere, isn't it?
It is the breakthrough. The MWR is designed to measure the thermal emission of Jupiter at 6 different wavelengths. Critically, these different wavelengths penetrate the atmosphere to different depths.
I see. So it's like peeling an onion layer by layer.
Precisely. By simultaneously measuring these varied emissions, Juno essentially creates a three-dimensional thermal map, allowing scientists to see through the visible cloud tops and peer down hundreds of kilometers into the deep hidden layers of the atmosphere.
So it's not just a surface reading. It's a topographical map of temperature and composition depth. That's true vision through the clouds.
It really is. But amidst all that high-tech engineering, there is a lovely human element in the story of Juno. The source material talks about the camera, JunoCam.
Right.
The initial directive from NASA was purely scientific. They didn't mandate a visual camera for public outreach.
I love that story. The team basically overruled the directive, saying something like, we just can't imagine going all that way and not having a camera. They insisted on keeping it on board.
And thank goodness they did. JunoCam has delivered the spectacular, visceral visual data that has captivated the public. While the technical instruments are drilling down into the gravity and microwave data, the camera is taking us all inside Jupiter to see what this environment truly looks like.
We get to see the strange phenomenon, these massive atmospheric features up close.
Right.
But to get that data, they had to cross a monumental boundary, a high-risk journey characterized by immense physical dangers. Let's talk about the approach itself. What was the most terrifying part of entering Jupiter's domain?
The terror starts when Juno crosses the magnetic boundary, what physicists call the bow shock. It's the point where the supersonic flow of the solar wind just slams into and is deflected by Jupiter's massive, dominant magnetosphere.
That sounds like a physical shift in reality.
It is. At that specific moment, the instruments registered an incredible sound, a very different roar. It's been described as a kind of Halloween sound, full of shrieks and whistles.
Which is entirely appropriate given the sheer power contained within that magnetic field.
Exactly. And the sheer scale of that magnetosphere, Jupiter's sphere of influence, is just mind-boggling.
How big are we talking?
Monumental. It is the biggest structure in the solar system, next to the sun's own magnetic field. Its tail extends perhaps all the way back past Saturn, maybe even further out into the system.
Wow.
This gigantic, powerful magnetic structure is what generates the primary danger for the spacecraft, the radiation belts.
And this is why we call Juno an armored tank. The radiation environment is not just bad. It is literally the most dangerous environment in the solar system for a piece of hardware.
It's the orbital gauntlet, a region that mission planners were deeply afraid of because no one had ever passed through it so close to the planet. It was described as sending the spacecraft into a shooting gallery where the bullets...
Energetic particles.
Right. The energetic particles trapped in the magnetic field are moving at almost the speed of light. They are powerful enough to instantly scramble and destroy unprotected electronics.
So how do the engineers ensure survival? How do they armor this tank?
The critical instruments, including the central computer and the high-precision clock, are housed inside a special container, a titanium vault.
Oh, well.
Yes. This vault is constructed with thick walls of titanium, essentially encasing the sensitive electronics in heavy metal to shield them from the energetic particle bombardment. It's like a bunker for the heart of the mission, weighing hundreds of pounds just for protection.
Surviving the shooting gallery was one thing, but the final terrifying moment was orbital insertion, the make-or-break burn that decided the fate of the entire mission.
The criticality of that single event cannot be overstated. It was described by the mission team as the hardest thing NASA's ever done.
That's a high bar.
It is. Juno had to precisely fire its main engine at the right time for the right duration, slowing it down just enough to be captured by Jupiter's gravity into a polar orbit.
And if the burn had failed to fire, or fired incorrectly, what was the risk?
The threat was existential. If the burn was off by even a small amount, the spacecraft would miss orbit entirely, slimshotting right past Jupiter and heading back out into the deeper solar system. Gone. It would take decades to come back around, and by that time the spacecraft, having already been exposed to the harsh environment and the deep cold of space, would likely be broken and useless.
So years of work, billions of dollars, riding on a terrifyingly precise burst of fire.
Absolutely.
Incredible. But Juno made the burn. It settled safely into its eccentric polar orbit, protected by its titanium armor, and began looking outward at the atmospheric violence before turning its eyes inward.
Exactly.
So, now let's talk about the findings. Section 4, the atmospheric violence, which includes the spectacular aurorae and the completely unexpected geometric cyclones.
The spectacle is a direct consequence of the immense energy flowing through the Jovian system. Jupiter is an extreme weather machine. We're looking at storms, like the Great Red Spot, that have lasted for hundreds of years.
Unbelievable.
We see winds that routinely clock in at 3 times the force of the most devastating hurricane on Earth. The atmosphere is a constantly boiling, churning maelstrom of gas.
And visually, nothing is more spectacular than Jupiter's aurorae. They glow with an intensity and coverage that dwarfs our own planet's northern and southern lights. What is the precise mechanism driving that stunning luminosity?
It's largely driven by Jupiter's moon Io. Io is the most volcanically active world in the solar system. It is constantly erupting, spewing vast quantities of gas, mostly sulfur and oxygen, into space.
Okay.
These gases become immediately ionized and trapped within Jupiter's immensely strong and rapidly rotating magnetic field.
So those gases become massive sources of charged particles just floating in the magnetosphere.
Exactly. But here's where the power comes in. Io acts like a gigantic dynamo. As Io orbits, it drags a massive electric conductor, what we call the Io flux tube, through the planet's magnetosphere. This interaction generates a staggering electric potential.
Wow.
These charged particles are then accelerated to incredibly high energies, practically light speed, as they stream down the magnetic field lines.
And where do those highly energetic particles end up?
They slam into the thin upper atmosphere near the poles. This constant bombardment excites the atmospheric hydrogen, causing it to glow fiercely in the ultraviolet and visible spectrum.
And what's truly fascinating is that These effects are caused by electrical currents flowing into the atmosphere.
Currents that can reach millions of amperes. We can actually see the footprints of Io and sometimes Europa in the aurora images, where those flux tubes terminate and deposit their colossal energy.
We are witnessing million-amp electrical currents bombarding an atmosphere and making it luminous. That's a phenomenal way to visualize magnetic power.
It truly is.
Now, Juno's orbit also gave us a view that no other spacecraft has ever had before, flying directly over the poles.
This was unexplored territory. Juno's close polar pass provides details at a scale never before achieved. And when you send instruments into a brand new region, you always expect discovery, but the findings at the poles were entirely unexpected.
Which were the geometric cyclones.
The geometric cyclones. This sounds less like chaotic weather and more like highly structured physics. Tell us about these bizarre stable vortices.
At both poles, Juno observed massive vortices, huge hurricanes that are packed together in a remarkably precise, stable geometric pattern.
Okay, so a pattern.
On the North Pole, they found 8 cyclones arranged around a central storm, while at the South Pole, they found 5 massive vortices surrounding a central one, creating a near-perfect pentagonal structure.
A pentagon of hurricanes.
Exactly. And the stability is the real mystery, isn't it?
It's the profound puzzle. On Earth and even on Saturn, when large vortices get close enough, they typically merge into one larger, single entity.
They collapse.
Right, but these Jovian geometric patterns have been monitored for years and remain locked in place. Scientists believe the stability is due to the deep, localized magnetic and fluid dynamics at the poles, potentially involving unique types of wave propagation.
Like planetary-scale Rossby waves.
Something like that, yes, that keep them from collapsing into each other. It's the first time anyone has ever seen such a stable geometric pattern of giant cyclones on any planet, or even in fluid dynamics experiments on Earth.
The idea that planetary chaos can organize itself into such sophisticated, repeating geometrical structures is just captivating. It truly shows we still don't understand the rules of gas giant fluid dynamics.
Not at all.
Now, let's go deeper into the atmosphere itself, specifically in pursuit of one of the universe's most important ingredients.
Water. The quest for water is foundational. Water is essential to life as we know it, but its abundance inside Jupiter is also a critical clue to the early solar system.
How so?
Understanding how much water is locked up inside Jupiter helps us constrain models of where the building blocks of ice and rock were available and how far out the snow line, the point where water ice could condense, was located when the planet first formed.
This was a major objective for the earlier Galileo mission, specifically its atmospheric probe, but the results were highly inconclusive, and they caused decades of confusion.
They really did. What was the Galileo problem?
The Galileo probe was incredible. It dove directly into the atmosphere, making direct measurements. But it sampled only one single spot, located in a surprisingly dry, clear region of Jupiter's atmosphere known as a hot spot.
And what did that one dry spot imply?
Well, the measurements were so low in water content that they fundamentally contradicted every prevailing theory of solar system formation at the time.
So it threw a wrench in everything.
Completely.
Yeah.
The implication was that if that dry measurement represented the whole planet, then the building blocks of water weren't present when Jupiter formed, and the entire historical narrative was wrong.
So the limitation was that we couldn't extend a measurement from a single, potentially anomalous spot to the whole planet. We needed a global map.
Precisely. We needed a way to measure water abundance across the entire globe, circumventing the issue of localized dry or wet patches. And that's where Juno came along with its specialized instrument, the MWR, which we mentioned earlier.
Let's elaborate on the MWR's genius, because it overcame a seemingly impossible hurdle. It uses microwaves, right?
Yes, and the principle is brilliantly simple, relying on a common household item. Water vapor is opaque to the microwave part of the radio spectrum. That is why your microwave oven heats up wet food efficiently. The water absorbs the energy.
Okay, so Juno's microwave radiometer is essentially using that absorption and emission characteristic as a tracer for water.
Exactly. The MWR has 6 antennas tuned to 6 different microwave wavelengths. The longer the wavelength, the deeper it can penetrate Jupiter's dense atmosphere before it hits a point where the atmosphere becomes completely opaque.
I see.
By comparing the heat signatures received at these different wavelengths, scientists can deduce the temperature, pressure, and critically, the water concentration at various depths. It provides a true, high-resolution 3D view of the planet's weather layers and composition that was previously impossible.
And while using the MWR, the team detected something entirely unexpected related to water.
Right. Incredible, powerful spikes in the radio signals that had nothing to do with thermal heat.
These spikes were initially confusing. They were measuring the heat of the planet, and every now and then they would get an intense, sharp spike of radio energy. They initially dismissed it, thinking perhaps it was instrument noise or a cosmic ray hitting the detector, but they kept recurring.
And the realization was,
That these were powerful radio signals emanating from lightning storms in Jupiter's atmosphere, likely 1,000 times brighter and more energetic than the most powerful lightning we see on Earth.
1,000 times.
It's important because the detection of lightning is confirmation of specific atmospheric physics.
What physics does lightning confirm?
Lightning, according to atmospheric theory, requires the collision of different phases of water ice, liquid, and vapor to separate charges and generate the immense electrical potential needed for a bolt.
I see.
The MWR detection provided strong evidence that the physics required for large-scale electrical storms involving water is indeed happening deep inside Jupiter's cloud deck.
So Juno confirmed the existence of powerful atmospheric water physics. But we also have visible evidence of water chemistry right at the top of the clouds.
Yes. The images from JunoCam confirmed the visible evidence of atmospheric chemistry. We see what look like little white clouds, though little is relative. They are tens of kilometers across.
Right.
They're seen at the very top of the atmosphere, and critically, they are casting sharp, distinct shadows.
Shadows imply structure and depth.
They do. These are believed to be massive ammonia water ice thunderstorms. Juno's measurements strongly suggest that the atmosphere contains a mixture of ammonia ice and water ice, which, combined with the presence of lightning, means it is hailing or snowing ammonia water ice pellets on Jupiter.
A truly violent, complex environment.
Incredibly so.
That paints an incredible picture of the Jovian atmosphere.
Mm.
Million-amp aurorae, lightning 1,000 times brighter than ours, and immense ammonia water ice storms. It's hard to imagine surviving those conditions, but science isn't just observing them. It's doing its best to replicate them here on Earth.
And that takes us from the atmosphere deep, deep down into the interior to the conditions that create the very structure of the planet. We move into the realm of Section 6, the deep ocean of metallic hydrogen.
This is a fantastic bridge between astrophysics and extreme laboratory physics. Scientists are trying to replicate the immense pressure and temperature found deep inside Jupiter at the National Ignition Facility, NIF, in California.
Right. NIF is primarily known for its pursuit of controlled nuclear fusion, but its core function, the ability to focus incredible amounts of energy onto a minuscule target, makes it the perfect environment to create a little planet interior.
Previously, studying the conditions necessary to transform hydrogen into a metal, the immense pressures deep inside Jupiter, was only possible through complex theoretical models and computer simulations.
Right. And now they can conduct real physical experiments.
The ability to do this validates decades of theoretical work. The internal conditions of Jupiter are so extreme, pressures millions of times greater than Earth's atmosphere, and temperatures reaching thousands of degrees Celsius, that they simply cannot be replicated by traditional laboratory equipment.
Not even close.
Describe the process of making this transformation happen in the lab. It sounds like an astonishing display of focused power.
It is highly controlled, yes, and focused on an almost unimaginable scale. The target is minuscule. Scientists place only about 20 millionth of a gram of liquid hydrogen inside a tiny cone in the target chamber.
20 millionths of a gram.
Then comes the instantaneous firing of the lasers.
And this is where the sheer power factor comes into play.
Our sources emphasize this power concentration. NIF uses 160 powerful laser beams, 80 firing from the top, 80 from the bottom, which are all focused simultaneously onto that tiny target.
And the power.
The instantaneous energy delivered by these lasers, when they fire, is about 500 times the power used for the entire United States at any given moment.
500 times the electrical power consumption of the entire U.S., focused on 20 millionths of a gram of hydrogen.
For a few nanoseconds.
And this shot lasts for only a few nanoseconds, a few billionths of a second. What happens during that instantaneous burst?
The hydrogen undergoes a radical, swift transformation driven entirely by pressure. Initially, the focused energy creates an intense shock wave, compressing the hydrogen sample rapidly. As the pressure rises, the hydrogen is forced closer and closer together. At first, it remains transparent, acting like a compressed gas.
But then the phase change occurs.
Exactly. When the pressure hits a critical threshold, estimated to be around 2 million times Earth's atmospheric pressure, the hydrogen atoms are squeezed so tightly that their electrons are forced out of their normal orbits and become delocalized. They begin to move freely throughout the material.
Which is the defining characteristic of a metal.
It is, from a clear insulating gas to a shiny conducting metal in an instant.
Precisely. The material transitions into a liquid, shiny metal state that reflects light. This is the condition that reigns supreme in Jupiter's deep interior.
If you could somehow dive past the atmosphere and the immense pressure layers, you would enter what is essentially a deep ocean of fluid, shiny, metal, liquid, metallic hydrogen.
And this NIF experiment is the first time this exact condition, found inside a giant planet, has been successfully created and measured in a controlled laboratory setting.
It's a huge step. It validates the foundational physics necessary to understand gas giant interiors.
That is truly astounding, the ability to bring the center of a giant planet down to Earth for a nanosecond. But the true goal of Juno wasn't just to confirm the existence of metallic hydrogen, it was to use the gravity field to see what sits underneath that ocean, at the very deepest center of the planet.
Which is the core question, literally and figuratively, and brings us to the biggest scientific breakthrough of the mission, uncovering the core and rewriting the formation theories. The subtle measurements of Jupiter's gravity field are the ultimate diagnostic tool for the planet's entire formation history.
They don't have seismic sensors or internal probes. So how exactly does Juno measure the gravity distribution inside a planet 500 million miles away?
It's a brilliant technique relying on precision tracking. Juno has this unique, highly eccentric, close orbit that brings it skimming just above the cloud tops.
Okay.
The distribution of mass inside Jupiter, whether it's uniformly mixed or concentrated in a core, will subtly affect Juno's trajectory. If there is a dense concentration of material beneath a certain region, Juno will move in a slightly different way as it passes over.
It's being tugged infinitesimally.
Yes. By monitoring these minute variations in Juno's velocity and trajectory using a technique called Doppler tracking, mission controllers can measure Jupiter's gravity field 100 times better than ever before. It's essentially weighing the inside of the planet.
Revealing the density structure beneath the metallic hydrogen ocean.
That's
And that data led to the revelation about the core that completely surprised the scientific community. What did the gravity measurements reveal?
The gravity data revealed that Jupiter does indeed have a core, which wasn't necessarily a given. But more surprisingly, this core is not a dense, neat ball of pristine rock. It's described as a fuzzy core.
What does fuzzy mean in planetary terms?
It means the heavy elements, the rocks and ices, are not perfectly settled at the center. They are mixed, gradually blending outward with the fluid metallic hydrogen in compressed gas layers.
So no sharp boundary.
No sharp boundary. It's a dense region, estimated to be equivalent to about 5 to 10 Earth masses of material, but it lacks the sharp boundary scientists might have classically expected.
Wait, why were scientists expecting a pristine core or perhaps no core at all?
Because of the competing theories of formation, which we'll get to in a moment. For decades, one dominant theory suggested Jupiter formed purely by gas collapse, similar to a small star. If that were the case, the planet would be uniformly mixed, potentially lacking a centralized, massive core of heavy elements entirely. If there was a core, many expected it to be a pure, dense pocket of rock and ice that formed first and then stabilized, maintaining a distinct boundary.
But the fuzzy mixed core was a structure no one had truly anticipated.
No one. This fuzziness is a massive finding because it fundamentally tells us how Jupiter started its life, supporting one origin model over another.
Completely rewrites the script.
It does. It suggests that Jupiter did not start life as a pure gas object. Instead, it strongly implies that Jupiter started its life as a rocky, icy world first.
Okay.
Only after that rocky, tessy core reached the sufficient mass, that crucial 5 to 10 Earth mass threshold, did its gravity become strong enough to rapidly capture and hold on to the surrounding hydrogen and helium gas from the solar nebula.
And how did that mixing happen? How did that core become fuzzy rather than remaining a neat ball of rock?
One of the fascinating theories the sources discuss is the shooting star hypothesis. This centers on the violent, chaotic environment during Jupiter's earliest growth phase.
Okay.
The early solar system was filled with tiny grains of rock and ice floating in space shooting stars, essentially.
And Jupiter's immense gravity was just sweeping all of them up.
Absolutely. Millions upon millions of these raucous grains were captured. When they plunged into the developing atmosphere, they didn't all make it to the center. They burned up violently, creating intense light and heat high in the atmosphere.
Like an atmospheric delivery system.
Exactly. This process effectively deposited the rock material silicates and ices directly into the surrounding hydrogen-helium gas, leading to a constant turbulent mixing.
So the core isn't fuzzy because it's melting slowly. It's fuzzy because the heavy material was delivered and mixed during a period of violent high-energy bombardment.
Precisely. That violent, heterogeneous mixing of hydrogen, rock, and ice is what resulted in the dense, yet diffuse, fuzzy core structure we measure today. It paints a picture of Jupiter's early life as being incredibly hot, turbulent, and bright.
This finding, the fuzzy core, essentially settles a long-standing debate between two competing formation models for gas giants.
It really does.
Let's break down those two models and how Juno provided the definitive answer.
For decades, planetary science was polarized by two primary models for how giant planets form. The first was the gas collapse model, also called the disk instability model. This theory takes the vast amounts of gas present in the early solar nebula and suggests that gravitational instabilities could cause a localized region of gas to collapse rapidly under its own weight, much like a star forming.
What does that model imply about the core?
It suggests the planet is born big and quickly, largely from pure gas. In this scenario, rocks and ices aren't really a necessary part of the formation trigger. The planet starts massive, and any heavy elements are likely just minor contaminants absorbed later.
Meaning it wouldn't necessarily have a large, centralized, distinct core.
Exactly.
And the alternative, the model that needs a core.
That's the Pebble Accretion model, which is an accelerated version of the traditional core accretion model. This model posits that you must start by taking little rocks and pebbles, the foundational building blocks, and using the physics of the surrounding gas drag and gravity inherent in the nebula to clump them together quickly.
So the gas helps build the core faster.
Right. The gas drag speeds up the process, allowing grains to rapidly grow from tiny centimeter-sized pebbles directly into massive 100-kilometer-sized planetesimals within a short time window.
So if the fuzzy core is a massive mixed-density region of rock, ice, and metallic hydrogen, how does that support the Pebble Accretion model over the gas collapse model?
The existence of a large 5 to 10 Earth mass concentration of heavy elements at the center is the smoking gun.
Ah, I see.
It is evidence that Jupiter built a substantial solid structure first. The core was the necessary trigger. Only once that core reached the critical mass did it gather the surrounding gas rapidly. The fuzzy nature simply means that the accumulation process was high energy and messy.
If Jupiter had formed purely by gas collapse,
The gravity measurements would not show this structured